Hi, I'm Charlie Jackson. I'll be the moderator for today's SUSTEC webinar on technologies for a circular economy. Dr. Carol Gross is the program director for IEEE SUSTEC, and I'm Charlie Jackson. Again, I want to remind people why we're looking at the circular economy. In a world of finite resources, we need to think about a different way of doing business. The take, make, and dispose is not really viable. We need to work on reduction, reuse, refurbishment, and recycling. And this is from the United Nations Environmental Program. Then the other thing to remember is the role of IEEE. We want to ensure that IEEE's response to climate change is substantial, appropriate, and properly engages IEEE, its members, and the larger technical professions. This is what Seifer Rahman said when he was president. IEEE provides a neutral platform, and we will be a function as a technology provider. The webinar series is intended for a broad audience and for the general community with an interest in climate change and serving the needs of the profession and the public by increasing awareness and understanding of technologies. We're sponsored by the Future Directions and in particular the IEEE SUSTEC. And there is the SUSTEC conference, which will be in April of next year. This year, or this set, we're our third talk. Our next talk will be topics in circular electronics, restoring the atmosphere by removing excess CO2, and topic on reusing and recycling batteries. So the next talk will be September 11th. Ravinder Daya will talk about bendable electronics and sustainable technologies. And you can register with that or just go to the webpage. Today, we're lucky to have Alan Booker, who will give his second part of a talk with examples on regenerative systems that actually are rare, with many of them involving technologies that directly partner with life, such as quick expanding field of regenerative agriculture. In this presentation, we will explore examples of regenerative systems already in place, and then imagine what future technological developments can make this happen. This is a cut and paste here. This is the second part in a two-part series. And Alan Booker is the founder and executive director of the Institute of Integrated Regenerative Design. His presentations are eye-opening and fascinating. So with that, why don't we let Alan put up his slides and have him start.
Very good. Thank you for the introduction. Let me go ahead and get things set up here. I think we should be good to go.
Looks good.
All right. So yes, welcome to everybody who was with us for the little adventure in my first presentation. We did some lifting of trying to actually come up with technically rigorous definitions of regenerative and sustainable. Kind of pointed out that the UN definition for sustainable that a lot of people have been working against is more of a vision statement than a engineering definition. So we spent some time going through and laying the foundations. Then I gave a simplified version of the definitions for regenerative and sustainable. And I'm going to review those super quick here because, well, if we're going to talk about case studies in regenerative design, we kind of need to have a little bit of a grounding in what we mean, all right? So we won't be able to walk through all those details, but a quick review of those definitions will be important as we start to think about, our case studies. right? So, and it should be a hint here that I give you a picture of this tree as when we start talking about regeneration, because what we sort of looked at last time was when we developed the thermodynamic definition of regenerative was we found that life was our functional working example of regeneration from a thermodynamic standpoint and a technical standpoint. And so, this is our role model and also our benchmark for developing a definition of regenerative and sustainable. And it sets a rather high standard for us, right? So, because life is regenerative and sustainable. So we'll start with a quick review, right? Redefining regenerative and sustainable that we did last time. And I started off with a thermodynamic definition of regenerative, and that's useful in some cases, but in a lot of cases, that's not quite as actionable of a definition because it would require a lot of mechanical statistics analysis and so forth to show whether or not you are meeting this definition. And it had to do with actually creating regions of negative entropy, which resulted in patterns of self-organization, self-organizing systems that would regenerate themselves using available energy flows. They would take ambient materials and information, and they would create negative entropy and self-organize. And like the tree does, right? Like a seed of a tree takes energy from the sun and uses that to become a self-organizing emergent system. So that's handy in some cases, but what I was going to do is come back to our patterning definition of regenerative. And that is handy in a wider range of cases simply because what we can look at is the patterns that emerge from self-organization. In other words, we can look at the macro effects that are being generated and see if they meet this definition. So from a patterning perspective, a system can be said to be regenerative if, first, it harnesses ambient energy flows from its environment to power and sustain its own operation. And that can be in real time or near real time. That kind of rules out having to recruit huge amounts of energy from, say, burning fossil fuels. And we say real time or near real time. For example, nature does create its own storages. Trees store energy, plants store energy biochemically and so forth, and then use it a little bit later. What we're talking about here is not having to rely on millions of years old fossilized sunlight, but instead be able to do it in a time period that's in the same order of magnitude as the system dynamic, right? So we harness that energy flow, we thereby articulate and improve the internal structures and functional efficiency of the system, while also articulating and improving the nesting and distribution of relational patterns between itself and surrounding elements, participating in and supporting temporal and behavioral patterns that contribute to the larger system function, helping them increase in quality and quantity over time until the system itself and the larger whole that contains it move towards a dynamic equilibrium whose maximum complexity is bounded by the total energy, information, and material flows supporting it. In other words, it's all the fancy way of saying that here this energy flows through the system, a region of decreasing disorganization, or put the other way, increasing self-organization comes together, and all these patterns start to emerge. Patterns of its own internal structure and function, of interrelationships with the other systems around it, and that these patterns and cycles in which it participates become more rich. And the web of interrelationships that are beneficial it has inside of itself and with external parts of its environment increase over time until they kind of hit a saturation point, a max of which is determined by, well, the amount of energy, information, and matter that is available to the system, because it will come to some, dynamic equilibrium up there. All right, so that was kind of our patterning definition of regenerative, and the whole idea was to give us something that we could look at an individual system and ask whether that particular system was regenerative or degenerative. Okay. And then we said, all right, well, what about sustainable then, right? And I sort of gave a critique of the UN definition. Sustainable is, like I said, being more of a vision statement. And in the book that I'm just finishing up called The Dynamics of Regenerative and Sustainable Holons, there is this, very systematic laying out of the thermodynamic and pattern definitions of regenerative. Then we come down to sustainability. And so again, it's like we want a definition that can be evaluated at the individual systemic design level, instead of being like a global emergent attribute. So sustainability is defined as the ability of a system to, first, maintain a regenerative system dynamic over time. That is, that if we took our previous definitions of regenerative, a system can get into that state and stay in that state over time, right? Recover, number two, is recover to a desirable regenerative system dynamic when challenged with stressors. So technically what we're talking about here is at low level stressors, we get what's called a hormesis effect, which is the system adapts and becomes better, becomes a little stronger, adapted to its prevailing environmental situation. And then we have what we call a resilience response, which is the system can completely reorganize and go forward in a new system dynamic if the stressor is so large that it forces a system reorganization. And you can kind of look at that when a forest has, a major event come through it, it will basically reorganize, rebound, and come back to a regenerative state, although it may take a little while to do that. And then the third criteria is that the system should create environmental conditions conducive to both the perpetuation of its own regeneration, the regeneration of the system in which it is embedded, and the regeneration of systems with which it symbiotically exchanges energy, information, and matter. Janine Banyas, who's widely recognized as one of the pioneers of bio-inspired and biomimetic design, put it this way: life creates the conditions conducive to more life. And if it didn't, then life would not be sustainable. It would create conditions that were contrary to its own, continued existence. Therefore, it would become unsustainable. So this is our third criteria for sustainability, is that the conditions that we create have to be conducive to the perpetuation of the system and the regeneration of the systems in which it's embedded and the systems with which it symbiotically exchanges information, matter, and energy, which of course includes all the living parts of the biosphere that are affected by it. So there you go. That's our quick flying review, right, into our definition. So, okay. So when I was asked to do this two-part series, I said, oh, we'd love for you to do case studies for the second part. And I'm like, ooh, wow, okay. The challenge of doing case studies of modern technologies that fully meet these definitions of regenerative and sustainable is that they basically don't exist in practice yet. In other words, we set the bar, the tree that we looked at the beginning has set the bar pretty high. And our mechanistic reductionist design approaches that design beautiful things like this, watch mechanism on the right, well, they don't really meet that particular set of definitions. They are degenerative in that you can wind up this watch and let it go, and all the gears start to, to wear down. The mechanisms will eventually fail. They won't self-repair. They won't, use energy from the ambient environment to rebuild themselves. They won't do any of that. So they're not actually regenerative. They are degenerative, and we just try to make them degenerate more slowly, right? So what are we going to do then if I'm saying that there are not any, things I could look at and point out with modern technologies that I say, all right, we're 100% there yet? What I would say is, well, first let's look at some historical examples that actually met this bar, and I'm going to give you one. And then let's look at a couple of quick examples from regenerative agriculture that are coming close and talk about why they are. And then look at a few examples of building designs that exhibit attributes of regenerative and sustainable design, but they're not quite there yet. They're trying to move in that direction, right? And then I'm going to kind of give you something at the very end that is very much this around the idea of like, how do we think towards regenerative design? And we'll just see if I can get through everything today. Okay. All right. So, mechanistic reductionist design is degenerative and unsustainable, as much as, that's what we're trying to do in engineering school. A lot of cases. We got some work to do, and it's, to me, quite exciting that we can learn from how life does regenerative, and therefore eventually learn how to create sustainable systems, right? So what I wanted to start with is the Ahupua'a system in Hawaii as an example of something that actually was regenerative and sustainable. And the Ahupua'a system was the system of watershed management that the indigenous communities had in Hawaii. And what I'm going to do is I'm going to pop up this diagram. This particular diagram comes from Bill Mollison's Permaculture Designer's Manual. And I'll give you one other diagram from a more recent scholarly work in the next slide. But what happened was, you can think of these volcanic islands of Hawaii. The watersheds were this little slice that started up at the top near volcanic areas, and worked all the way down into the ocean. And what you see here is that this slice was managed by a village that lived there, and it was so closely connected to how the landscape was working that the people themselves ended up being a keystone species in that ecosystem, and all of the technological elements that they put in place actually deeply supported the life around them. And so they acted as a mutually symbiotic element of the surrounding environment. They built their buildings out of the materials found at hand, and when the buildings were done, they composted right back in place. There were no toxic materials or toxicants we had to work with. It's actually a really fascinating system, starting with upland forests that serve all kinds of functions. They would leave these to hold the land, but also to provide other ecosystem services. Then they would come down and they would do some stream diversion laterally to help hydrate those mid slopes and provide all the water they needed, but it also helped to enhance, whereas the water wanted to run right down the middle of the valley, they would spread that back out and they would enhance all the ecosystems along those mid slopes while putting their village there. And then, there's this whole sequence of things all the way down into the ocean of how they were tending the land, and every part of this watershed from the top to the bottom was actually benefited from them being there, while at the same time they led an incredibly rich life, resource rich life. And and people are saying, oh, well, that's very primitive and so forth. Our best guess is that they had to labor something like 2 hours a day to meet all of their needs, shelter needs, clothing needs, food needs, water needs, all of it. And the rest, they could just enjoy. So we can scratch our head and think about, do we really think that's primitive? Um, and yeah, they didn't have the internet, but maybe that was not a completely, maybe it wasn't a completely bad thing. So I wanted to start off and just say that human beings have a long history of creating systems like this that were so well integrated into the landscape that they really did meet the full definitions of regenerative and sustainable. And there's a lot of these kinds of case studies we could look at. And by the way, here's another example, or excuse me, diagram of the Ahupua'a system, right? This one, the reference here is in the lower right now, in an article called The Hawaiian Ahupua'a Land Use System, Its Biological Resource Zones and Challenges for Silvicultural Restoration. And basically because the indigenous people of Hawaii were working with nature instead of trying to power over it, they succeeded in creating a village system that met all their needs, yes, helped the surrounding environment thrive, and actually met all of our rigorous definitions that we were just considering. So, it's like we know how to do it. It's when we started to move into a design ideology that said we were separate from the natural world and that we should look at it instead of a partner, we should look at it as merely a resource base and that we knew better than it did. Well, it turns out that nature has close to a 4 billion year R&D program on how to do regenerative sustainable design. And we popped up and decided that we obviously knew how to do it better. And any even-handed rigorous comparison of human technologies and nature's patterning shows that we ought to be approaching everything with a lot of humility because we're making a mess of things. We basically create systems that generate huge amounts of positive entropy in a lot of areas. We take a lot of energy to create a manufacturing process to reduce entropy in one little place, and then we create a lot of byproduct entropy, and then the things that we manufacture in our factories typically run down and end up in a landfill. So yeah, and I always tell people, go show me the landfills in the old growth forests. They don't exist. Everything is recycled with near 100% efficiency. All right. So, well, what about regenerative agriculture? And in the 1990s, when I first started studying regenerative and sustainable design, by the way, there was no grad programs in it at that point in time that I could find. I started looking around and realized that the people that were the closest to something that I could look at and say, yep, that's getting to regenerative and sustainable were some of the people that were doing the early investigation in regenerative design and permaculture and so forth. And when I started looking at it and realizing that they had systems that were working and were functional, I was like, wow, why are they kind of there and a lot of other technical fields aren't? And I think the answer kind of popped up as obvious. Well, they started because what they were doing was working with life, which is the example we have on the planet of regenerative and sustainable design. And so what they realized was if you partnered with it, instead of doing what industrial agriculture does, which is try to make it act like a machine, right? Then you could get somewhere pretty fast because nature wanted to be regenerative. And if you like aligned with that regenerative impulse, as Janine Banyas put it, align with life's regenerative impulse, then you get a big tailwind in what you were doing. And so what had happened for a long time was industrial agriculture's idea was we want predictable, we want it to behave the way we want it to behave. Life is unruly. Let's see if we can make it behave. And so they started to create it almost to try to drive it towards a machine model. The more they did that, the more their crops became sick, the more they had to intervene with large scale chemical interventions in order to keep a crop production happening. The more they had to, till, the more they had to irrigate, the more they had to do chemical applications of fertilizers, the more they had to apply biocides in order to keep the system, quote unquote, behaving the way they needed it to. And so regenerative agriculture. So, well, what if we didn't do any of that? What if we actually like saw how life wanted to work and said we're going to work with that instead of against it? And there's a lot of great examples these days of people going in this direction. We'll give two really interesting ones. One is quite famously Joel Salatin at Polyface Farm, um, made famous by Michael Poulin's book, The Omnivore's Dilemma, but since then has become known internationally for Polyface Farm. And part of the reason that Polyface Farm has become so well known is because he started with degraded land many years ago, and by basically mimicking a natural ecosystem pattern of herd grazing, he created a high fertility pasture with no chemical inputs. He produces very exceptionally high quality food that is nutrient dense and at the same time is restoring the local ecosystem. And you see here also in the lower left, the chickens come in behind the cows as they rotate, and they mimic the birds coming behind the ruminant animals in a savanna ecosystem. And they break up the cow patties, they spread it out, they break the fly larvae cycle and so forth, and they produce an incredibly high omega-3 rich egg as a result, as a byproduct. And so you have multiple yields stacked in the same way that nature would do. And their products are in high demand, and they have been consistently profitable without external subsidies. And if you've looked at modern industrial agriculture, that's quite a statement. Very, very little of modern industrial agriculture is profitable without subsidy, right? All of their neighbors that are using conventional industrial agricultural approaches require big subsidies to be able to even break even. Here, they are able to be profitable without any government subsidy. So they are also economically regenerative. They don't have all the costs of chemicals and plowing and extra feedstock and trying to finish with grain imported from external sources. They are aligning with natural systems and creating a regenerative agricultural system. And so this shows how we can move past some of the industrial ideas and back towards working with natural systems, but doing it in a modern context. Another example is Mark Shepard at New Forest Farm. He produces a variety of perennial crops and animal products on a farm designed to mimic the native ecosystem. So he looked at where he was on the land and he said, well, what kind of trees want to grow here? What kind of animals want to live here? And let's do a farm that basically takes and mimics that pattern, and began to put patterning on the land. And you can see some of the beautiful patterns that are put here. They're very organic patterns that work with the lay of the landscape to passively harvest water, spread the water out so that the need for irrigation is drastically reduced. And again, another example of regenerative agriculture requiring no toxic chemicals and producing a very high quality product. So, yep, this was the place where we were starting to see, the fact that there's now a growing demand for food of this quality as people understand that low quality food is having huge health impacts. And so cases of getting closer to being a fully regenerative system. Right. All right. So, yep, this is an IEEE webinar. So, okay, where's the little more technical, engineered examples? And so, I was sitting here thinking about that, and going, okay, what kind of example can I give? And I do work with ILFI, the International Living Futures Institute. I'm Living Futures accredited and have worked on some projects that are associated with this thing called the Living Building Challenge. And so there's that word again, right? Life living building challenge. And the Living Building Challenge was created by Jason McClendon a while back, who asked, what if a building could be having a building on a footprint of land could be as ecologically sound and regenerative as having the native landscape there, a forest or a meadow or prairie savanna ecosystem, whatever would have been indigenous to that place. What would that look like? Could we take that as a goal? And so he created this thing called the Living Building Challenge. There are currently somewhere between 30 and 40 full Living Building Challenge buildings on the planet. There are a lot that meet some of the requirements, but there are still less than 40 that meet all of the requirements. And so what they basically said was, what if a building acted like a flower? Which again, it's like biomimicry, right? What would it look like to create modern technology that was patterned after living examples of sustainable regenerative design? And so they said, well, what we're going to do is we're going to break it down into a number of categories, including place, restoring a healthy interrelationship with nature, water, creating developments to operate within the water balance of given place and climate. You have to actually generate all of your own water on site that's going to be used, and you're not allowed to create any wastewater. All water has to be returned to potable standard on site. There's no sewage, there's no septic. You have to actually, completely handle the water cycle on site. And it's actually not as hard as it possibly sounds. Energy, relying only on current solar income. Technically, they say you need to generate 105% of your energy consumption averaged over a year. We'll come back to that in a minute. We need to create health and happiness for the people. The materials have to be completely biocompatible. That is, that they need to be toxin free and compatible with life. They need to have, you need to look at their embodied carbon footprint and so forth. And you need to look at your waste and create no waste. It needs to support equity and a just and equitable world. And it needs to be beautiful and support biophilic interactions by the people. And so one of my favorite examples of a Living Building Challenge building is this one. This is the Visitors Center at the Van Dusen Botanical Garden in British Columbia. And well, the first thing I want to do is just like pause for a minute and basically say, oh, it's just a beautiful and organic building, right? And so it shows an example that when you start moving towards this sort of patterning, that you end up with something a lot less sterile than a lot of the rectangular boxes that pass from modern agriculture, modern architecture. And so here is a bit of a technical diagram showing how I believe it was Perkins and Will did this one, how they did the energy systems and the water systems and worked with the flow of energy and water through the systems. One of the things that's interesting is this oculus at the center of the visitor center acts as a solar chimney. And that's sort of inspired from the way that termite mounds self-regulate in the deserts of Africa. So you get a passive chimney effect and a lot of passive ventilation driven by the ambient energy flows. You also get rooftop rainwater collection, and you can see that they bring the stormwater in, that they have a bioreactor to do their black water treatment. They can bypass to city sewer if they have to, if the bioreactor goes down. But under normal conditions, that goes back to a percolation field, and all that water is returned to the land where it landed during the rain, right? And they do have a backup, city water supply, but they're able to do a lot of it from the water that just came down. You can also look at all the different ways that they're using energy. And boy, I could go through this for a long time, but you get the idea of what they're trying to do is see if the building can interact with the land in a way that the energy and information and material flows of the building are an integral symbiotic part of the landscape. And think about that. Here, by the way, is a view of the inside of that solar chimney from the inside, and that that solar chimney is heated. That metal thing that's hanging there is actually heated by the sun, and that creates the solar chimney effect. And this is the outside looking at that oculus, and you can see they have a green roof, and it actually is connected in on the ends to the landscape, so that you have wildlife traveling freely over the roof. Yeah, they have all kinds of wildlife that they know that uses this and lives right in the area that comes across the roof, and that everybody that works there has gotten to know the animals that move back and forth across the roof of their building. So that is an example of like this thinking around living building challenge, and one quick example of a building that's moving there. There's a lot of other fun ones to go look at and study, because if you're doing living building challenge, then you're required to document and share what you learn through the process. It's part of living building challenge. So what I want to do is kind of close off with modeling regenerative thinking a little bit by talking about the challenge of heating a building. And this one came up to me because this was one of the living building challenge projects that we were looking at and doing conceptual design around. And the challenge turned out to be heating a full living building challenge building. In other words, the project was looking at building a full LBC building. Again, we said there's fewer than 40 of those in the world. And so we were looking at the problem of heating an LBC building during the winter. And so, of course, we started with, high performance building envelope and passive solar design, but additional heat input during periods of extreme cold, when there was also overcast skies, that's still going to be required, right? So, okay, where does that extra heat come from? Well, the first idea is, well, we'll just do we'll just make a heat pump that runs on electricity. The challenge you get, of course, is that the exact moment you need this the most is the moment that your solar panels up there are looking up and seeing nothing but gray overcast and producing almost no energy, right? So, here we go. When I looked at this and did my analysis of it, I said, what I want to do is I want to use a technology called a carbon negative mass heater that would be powered by wood. And the specification for a carbon negative mass heater is something I came up with. And so I said, here it is. Here's the technically rigorous definition for a carbon negative mass heater. And we call it a carbon negative mass heater because we can heat while actually sequestering carbon, okay? But the problem is that IL5's current standards don't allow for combustion of any sort, because they're saying, well, we want full electrification, and because that's the way we're going to do it. So when I said I want to use a carbon negative mass heater powered by wood, they said, no. What you need to do is you need to, quote unquote, right size the solar array instead, which was make the solar array a lot bigger And then, of course, what they didn't say but was implied is make the battery array a lot bigger, because you're possibly, during you might have to have multiple days of solar autonomy in this system to be able to electrically run a heat pump. Okay, so the suggestion that they were making assumes that the extra power, because most of the LBC buildings that have been done, they're grid tied. Okay, so the way that they were thinking is, that's why there's 105%, right? They assume that the extra power you produce in the summertime, when the sun is just nice and out there and beating down on you, be pumped back into the grid. And then in the wintertime, you can pull from the grid, right? And as long as net you produce 105%, that you're good. In other words, they think of this as fungible energy. You pump it into the net and pull it back out. And if the grid, and what they're doing, though, for those of you who are keeping the score, is they're externalizing all of the effects of the grid, right? So, but the problem was, for this particular project, there was to be no grid connection. The whole thing was 100% off grid. So that whole thing was not even possibility. We couldn't do net metering for this because there was no grid connection. But what we ended up showing was that even if this was going to be grid tied, the carbon negative mass heater would still have been the better option. So, see, Charlie's jumping in. Charlie, you got something? Okay. Oh, wanted to make certain we were okay. So let's go through it real quickly, because there's this basically has us asking some questions about how do we assess things, and what boundaries do we draw around a system that we're assessing in order to assess whether we're being sustainable and regenerative. What I turned out showing them was that when we looked at and amortized all of the costs of upsizing the solar panels and the batteries and everything else, you have to take into account an awful lot more than you at first appear. So, the first thing we looked at is, since we're generating 100% of our energy of the building in near real time, energy efficiency is critical. And for those of you who are in this field, you probably heard of EUI, energy use intensity. It's calculated in different units, but in the US, we typically use kilobTUs per square foot per year. In other words, for every square foot of the building you have, over the course of the year, how many kilobTUs of energy do you use? All right, and here's the quickie for all of the engineering types, right? You convert everything into kilobTUs, whether it's a kilowatt of electricity or cubic foot of natural gas or gallon of propane. There's all the conversion factors. You add up all of the energy, you divide by the square footage, and you get an EUI in kilobTU per, per square foot per year. Okay, and we get a number. And by the way, the problem is, when you look at that and you do that calculation, what do you have? You have what we call a site EUI. That is, it's the energy use intensity of what's going on just with your site. It assumes that basically the energy that arrives at the meter magically appears, and you don't have to account for it in your in trying to figure out whether what you're doing is good, bad, or ugly. So there's another category called source EUI, where we go all the way back to the source. This, of course, if it's electrical, means that we have to take into account distribution, transmission, generation losses, and so forth, right? And so if we could go back to and look at, we have to extract coal. If we're doing coal fire, we have all these losses, and that gives us, if we go all the way back and we look at how many kilobTUs of energy we use from source to delivery, we have a source EUI. And those numbers can be quite different. Here's a table of EUI values that are typical for different building types. What I find interesting is that the most energy intense building per square foot by far is a fast food restaurant. Um, and that grocery stores, convenience stores with gas stations, hospitals are, come in right behind that. And non-refrigerated warehouses are down towards the bottom, right? And look at the difference between source and site EUI for all of these. Oftentimes the source EUI is well over twice the site EUI. So drawing the boundary around things and trying to do an example. This is why the definitions we're working with are, they say that we have to take into account this larger system in which we're embedded, right? And by the way, the goal for one of the most aggressive buildings that I was working on was to power itself fully from site with no other connections. And when we looked at it, the EUI, which would be the source and site EUI, since there's no remote connection, we were looking at a EUI of around 5 to 7, right? And by partnering with the living world around us and working with that. So what if we weren't allowed to externalize, right? What if we could not take our unsustainable and degenerative stuff and hide it in the third world, which we have a tendency to do, right? What if we couldn't hide it down the road at the gas fire plant? What if we had to do scope 3, which is emissions of the entire supply chain or service, like all the feeders that come in? So, we started looking at this and saying, what I want to do is I want to produce the biomass on site, and I want to burn it with a rocket mass heater, which is the only heater technology we have right now. I wish I had time to unpack this. It's an amazing technology, and it's very simple to build with very low-tech components. Its systems efficiency is off the charts. The one on the right, just to give you an example for those, this is a modular home of about 1,800 square feet. And this particular rocket mass heater installed here heated this building, always keeping it above 68 degrees Fahrenheit for an entire winter in Montana on 0.6 cords of wood, whereas most people nearby use 5 to 7 cords of wood to do the same thing. So, and the system output is basically carbon dioxide and water vapor. So I'm gonna run through the case study super fast, and then we're gonna wrap it up. So to prove that that we were several orders of magnitude better than the solar alternative, when you took in a scope 3, we did a case study. In this case study, I was assisted by a carbon combustion chemist who had a couple decades of tenure from the EPA, and she ran these numbers you're going to look at. Right. We said, what we're going to do is we're going to grow poplar wood local. We're going to harvest 40% of the biomass, this new biomass every year. We're going to combust it in an 8-inch rocket mass heater core. That will allow us to burn 6 hours per day for 120 burn days per year. That actually heats several buildings. And we're using 6.67 pounds of fuel per hour. Okay. And here we go. This is the system flow, carbon flow diagram. We did a full thing. I don't have time to unpack it, but we're looking at how the tree pulls carbon from the atmosphere. It goes through this whole cycle. And when it burns part of it, we put part of that carbon back into the atmosphere, but part of it ends up in the soil, and part of it ends up in the tree growth, and so on and so forth. And we were looking at this now from a systemic standpoint. And so we said, well, here are the inputs. And again, I'm not going to have time to go through all the numbers, but here are the numbers that pop up, BTUs per pound and all this sort of stuff. For the input side of the scenario that we just ran. And then here's the output. And the numbers I want to look at are down in the lower in red. Okay, what we come down to is, given that case, the rocket mass heater is going to produce 1,446 pounds of carbon emission into the atmosphere, but in operation of the system as specified, it would actually sequester approximately 20,000 pounds if we did not use grazing animals as part of the silvopastoral system, and a lot more than that if we did. So he said, let's just assume we don't want the complexity of grazing animals. So, and so forth. And there's references down there for all these numbers in small print. So everything here is referenced. And so here is the case study summary, right? We could produce 30 million BTUs annually, release 1,446 pounds of carbon dioxide, but all of that is carbon dioxide that had just been pulled down earlier that year out of the atmosphere, while actively sequestering 20,000 pounds of carbon dioxide by biomass production every year, for a net of over 18,500 pounds of carbon dioxide sequestered per year of operation. Soil organic matter building at about 5.5% annually. Basically, what we figured is over the lifetime of the system, we'd be something like sequestering 370,000 pounds of carbon dioxide by using a technology that actually worked with and regenerated the life and the on the site, right? This is not applicable to every site, but for this particular site, it was highly applicable. So when we looked at this and compared it to the footprint that would have been there if we had put a large, solar panel on there and everything else, all of the mining of materials and so forth, we calculated that we were, well, it's hard to get it, but we were at least 2 orders of magnitude better in carbon sequestration, embodied pollution, embodied all of it, right? So carbon negative, so it ended up having a radically smaller whole system footprint than what was originally thought to be the right regenerative pathway, right? So any system that we use that uses energy generated offsite must include the amortized pollution, carbon, energy footprints of the energy generation, transmission, distribution systems, along with the footprints of all the infrastructure required to support it, right? So complicated high-tech systems aren't always the best solutions, since they often hide a lot of externalities, and we need to start thinking in that whole system standpoint in order to be able to really create systems that are robustly regenerative and sustainable. So quick little view of contact, and then I'll hand it back so we can have maybe a few questions.
Okay. There are a number of questions. I wanted to start off with a fairly simple one. If I look at cotton farming, I've always heard how it destroys the soil as time goes on.
Yes.
And so how would one think of cotton farming in terms of the destructive way, the sustainable way, and a regenerative way?
Yeah. The challenge with cotton farming, and there needs to be a lot of research on this, because cotton has been turned into a large monoculture crop, right? And okay, go out and find in nature, in a temperate zone where we tend to grow cotton, go find 10,000 acres monoculture of cotton, right? Nature doesn't do that kind of pattern. We want to do it because of economies of scale. And as soon as we do it, nature basically views that as a problem. It says, oh, look, this is all sick over here. It's all growing only one thing instead of a biodiversity. I can fix that. And it goes in and tries to fix it for you, right? So what we would end up having to do is actually intercrop and rotate in order to be able to do it. It's doable, but it would look different, and it would involve intercropping and not doing huge monocultures, because as soon as you do a monoculture with plowing, you're in it. You're in full industrial agriculture, and you're going to be doing chemical warfare. That's just where you are.
That's a good term there. There is one question in the Q&A, which is, can you elaborate on how regenerative self-heating electric grid works?
Whew. So there's a whole lot about like the question, how do we make the current version of the electric grid regenerative, right? Because nature doesn't do anything like that exactly. Nature tends to do distributed solutions. And the reason is that feedback loops are small and tight, and therefore control decisions can be made, and there's not a lot of loss in transmission distribution. So a power generation, of course, we've done power generation the way that we ended up as electrical. So I'm an electrical engineer by training, right? We did it that way because steam plants, steam engines have economies of scale, right? We wanted to be able to do the big, huge, multi-gigawatt, coal fire plants that are now being replaced mostly by gas plants and so forth. The whole problem is that all of the infrastructure, all of it, is degenerative infrastructure. So there's a whole lot of head scratching that has to go on there. And I think a lot of us have got to start sitting down and thinking about, how do we use massively less energy at the places of consumption? And therefore, how do we begin to distribute production out? If you ask me to go in and put heating and power on a typical suburban house, that's a very heavy lift because it consumes so much. Its EUI might be, site EUI might be 60 to 80. As soon as we design a building, which we've done, that has a source or site EUI of like 5, now we're in an entirely different problem set, right? We've reduced it by an order of magnitude, and now distributed generation becomes a lot more reasonable, right? I think we've got to look at it that way.
Okay, that's good. Let's see, Wei Jen, can you take over for the rest of the questions? I need to leave for another meeting, it turns out. I will, while Wei Jen's seeing if he can do that, I'll point out somebody mentioned that in Iran, they've had these solar chimneys for years. And
Yes, for actually a couple thousand years we know of, yes.
yeah, which is something I'd heard about recently. Um, so anyway, I need to sign off now. So Wei Jen, if you can take over. You're muted right now.
Yep, that is thank you very much for a very interesting presentation. And so when we look at it, okay, that is the basically, okay, well, they talk about you are in the Q&A box, is that right? So that the Q&A box, the only one question, one open question that it's a electrical grid. So that is only one question that you have answered. And I don't see any other question over there. So
Yeah, I see that Nick has said something about, solar constant 1 kilowatt per square meter. Solar panels average 20.
yeah, that is from
Right.
the chat side.
Yes.
But not
Yeah, I
from
was
the
just looking
Q&A
at that
side.
and saying, what's interesting to me is that from all of that is that we have been able to show that we can reduce the consumption of the typical American home by something like 90+%, while actually, this is an important point, while actually improving the quality of life in the building. Right.
Okay.
So that's something I wanted to point out. It's like, we're not saying, oh, and you get to suffer, right? Oh, and you don't get, it's like, no, actually, because we're using things like radiant heating and other approaches like this and annualized thermal inertia, the buildings are actually reported subjectively by the people who occupy them to be more comfortable than the high energy buildings they replace. So I think that's a very critical thing to point out.
Okay. And then the other one is basically, okay, all this additional equipment, what will be the payback time, return on investment? Then
Yes.
how long will it take? And any maintenance is required. Okay.
Yes.
And then also with the current climate change, we see a lot more drastic the weather pattern. Will that increase the risk of this kinds of investment?
Yeah. I mean, I've been involved in the response here in Western North Carolina to Helene, and we're looking at all the infrastructure that got just plowed under by the, like miles and miles and miles of road infrastructure, power infrastructure, water infrastructure, sewage infrastructure, communications infrastructure, all just got plowed, right? So yes, if we put infrastructure into vulnerable locations, we're going to need to count on it being basically needing to be constantly replaced. So I wanted to point out real quick on this that I didn't get a chance to do it on this carbon negative mass heater. Okay, great. What does it take to build? It requires some double wall steel chimney pipe. Okay, the rest we can get on site, and a little bit of a locally produced fire brick. That's it. Okay. Oh, and a steel drum. We're using a steel drum. That's it. Okay. That, if it's properly maintained, has and it can be maintained locally with no external supply chain for 50 to 75 years. The fuel is available quite literally, and we can grow it right outside the door. Highly resilient. Okay. The embodied pollution in that is extremely low. Everything except for the steel pipe can go right back into the land where it came from, right? So there is the waste is a tiny fraction. There is not this huge distribution, transmission, generation infrastructure spread out all over this place. It's vulnerable, as it comes down mountain valleys like it does here, and it gets washed out by floods. It's like, that is, from a regenerative thinking standpoint, it's like we need to do the full scope analysis. How resilient is it, and so forth. And sometimes we get excited by doing big, huge infrastructure projects when you look at the way nature solves the same problem, and nature doesn't do it that way for reasons, right? It is not always the most efficient way to do it. And so that's just part of the reason I wanted to do that example of the rocket mass heater. Super simple, low tech thing. It works like a champ. It's more comfortable, and it's incredibly resilient, and it's made 98% with locally available materials off the land, right? So yeah.
And then the other one is the question from Susan, is how much land is required to grow the fuel for one home with the rocket mass heater?
Yeah, so we've seen examples of where people on like a half-acre site are growing enough annually to be able to harvest it from their own site to be able to heat a home pretty well.
Okay.
So it's, like I said, it's not exactly something we're going to be using in every home in a dense urban core, but in a lot of places, it's actually, and maybe what I point out is the more rural you get, the more expensive it is to pipe electricity out, down every road all the way down to the end of, every little county road. And so here in that situation where there's a lot of biomass being produced, then it's probably going to be a lot more cost effective, but also a lot more regenerative to use this kind of approach instead of trying to drag a transmission line all the way down to a distribution point and then distribute it out into an incredibly rural neighborhood, and then put a heat pump in to produce the heat. Yeah.
Okay, and then the other question from Carol is it possible to come up with a roadmap to switch to a regenerative economy, because this is basically from the current state that people
Yes.
that you utilized, and that basically the electricity or the system from the supported infrastructure. Then how can we basically convert it or switch to the regenerative economy?
Yeah, that is actually the question, isn't it? The reason is that the current economic system has three roadblocks I want to identify super fast. The first is that it is systematically predicated on growth. It will start to seize up if you don't get a growth of the economy on paper. And therefore, we have all been primed. I mean, every time we turn around and hear a politician talk about the economy, the next word out of their mouth is growth, right? And there's a reason for that. And it's because the economic system, the way it is currently based upon debt and so forth, it's designed for a growing system. And it doesn't function under a system that is in a conserving state. Therefore, we have to drive growth under the current economic system. As long as we're there, we've got that. Number two is that the current economic system allows huge amounts of externalizing of costs. And so somebody pointed out that modern corporations are externalizing engines. What they want to do is they want to grab all the profit, but all the costs that they incur through their action, they want to see if they can push it out on somebody else, right? So as long as we have an economy that allows for basically wholesale externalizing of costs, nobody has to pay the real cost of what they're doing. And therefore, the incentives are not aligned with by having to actually bear the real cost. And the third and final thing I'd point out is when we created the current economic system back a few hundred years ago, there was a simplifying assumption made. And it was at that point in time, because we were using a very small percentage of the Earth's resources, the natural resources of the Earth were modeled by our current economic system as an infinite source of resources and an infinite sink for waste. If you look at it, there's nothing in our economy that accounts for a cost of extraction of a natural resource, and nothing that really accounts for the cost of dumping waste back into the natural ecosystem. And so what we're going to have to do, and this is one of in the integrated regenerative design framework that I'm working with and have developed, the ecosystemic finance and economics is one of the elements of that. And what it basically says is that the biosphere is our primary economy. It's our primary source of wealth. And so when we do the accounting, we have to account for whether we are increasing our capital, primary capital, or destroying our primary capital. And that comes down to, are we regenerating the natural world around us, or are we destroying it? Because if we completely destroyed the natural world around us, how much wealth would we have left? None. As a matter of fact, we'd all be dead. And so it's like, that's what we call it the primary economy. It's like that the biosphere that creates the conditions that allow life, if we don't have that, nothing else matters. Literally all humans would cease to exist as a species. Mm-hmm. And so it's like to drill down to the root cause of why the current economic system is not capable of doing what it needs to do is because it doesn't account for the primary wealth of the planet. It ignores it and assumes that it's infinite and we can draw from it forever without an impact, and that we can dump waste back into it forever without impact. There's no economic accounting for that.
Okay, well, that is basically, we have a basic, the Nick talk about the power consumption in the different area that require the solar panel and the biomass. So yes, we understand that this is location dependent. And basically, okay, the other one is during your presentation, you talk about the solar panel. Mm-hmm. And then you basically push the surplus back to the utility grid and then come back. And then,
Yes.
so this is based the assumption that utility grid is there.
Yes.
So that is the basic, well, that is, it's a construction cost is already there. So that
Right.
how to balance out, and then how to account for that. You utilize the utility grid, then basically for the regenerated purpose. So
Yes.
how can we consider that part of the cost?
Yeah, I think we have to amortize it, right? There's no other reasonable way of doing it. You have to say, we're using this slice of all that infrastructure, and therefore let's amortize that cost down to each of those applications. Because what's going to happen is at some point in time, if we keep on adding more, they're going to have to build more infrastructure, right? So what's your share of that infrastructure cost plus the embodied carbon, plus the embodied pollution, plus all the other ecological footprints? And if we ignore that, we're ignoring the fact that if we keep on building stuff, eventually somebody's out there in the backyard building infrastructure to provide our demand, right? So I think we have to find a way of amortizing all of those footprints down to the points of use.
Okay, that yep, that is the basically okay. Well, what of course that is the basically the price structure is another issue, and then of course well, thank you very much for your excellent presentation. Carol, I'll turn back to you for a closing remark.
Yes, thank you so much. Thanks for to all our attendees for staying with us through the end here. We ran a little bit over time, but Alan, we deeply appreciate your presentation and the breadth of the examples you showed. I think it gave everybody some good ideas. We will reconvene on September 11 for a topic on circular electronics. So everybody, please join us again, and we will have more presentations after that, of course. So keep in touch. Alan, is it okay if I ask you if you can be contacted by anyone who has further questions?
Yes, we'd love to do that. And you can just contact me. My email is Alan, it's ALAN, at i2rd.co. No M on the end, just .co. Alan at i2rd.co.